Hello, everyone. Welcome to today's webinar. On behalf of the National Transit Institute, I welcome you and thank you all for participating. The National Transit Institute develops, promotes, and delivers training and education programs for the public transit industry in the United States. Today's webinar is based on TCRP Synthesis 149, Transit Signal Priority, Current State of the Practice. We are pleased to have as our presenters today Michael J. Walk and Paul Anderson from the Texas A&M Transportation Institute, Owen Kehoe, Transportation Engineer at King County Metro in Seattle, and Tim Lawson, Senior Transportation Engineer at the Toronto Transit Commission. Excuse me. Today's session will include the presentation and a moderated Q&A session at the end. You don't have to wait until the end to ask a question if you have one as the presentation is going. We just ask that you type it into the designated Q&A box, and then it will sit there and we will get to it at the end of the program. If for some reason you don't see your Q&A box, it should be a little icon by your Zoom controls, kind of near where the chat box is. People sometimes put the questions in the chat box. I will try to stay on top of that. It's easier to keep track of them if they are in the Q&A. So we just ask that you try to do that. Speaking of the chat box, you can talk to each other, and I will be using it to paste the link to the handouts in the event that you do not already have a copy for the presentation. I think that takes care of all my housekeeping, and without any further ado, I will turn the presentation over to Michael.
Okay, thanks, Lori. Just confirm that you can hear me okay, Lori?
I can hear you great.
Awesome. Okay. Well, thanks for joining, everybody. And this is Michael Walk, and I was the principal investigator on this research. I'm with the Texas A&M Transportation Institute. I've been there for about 5 years, and my background in research is in transportation technologies and transit management. And I'll be joined today, as Lori said, by Paul, Owen, and Tim. Each will introduce themselves, briefly when they start their speaking parts. And we just want to go ahead and dive right in to give you a feel for what you're going to see today. This presentation, this webinar is about transit signal priority. And folks may be on a very different planes when it comes to the language used and what even TSP actually is. And so we're going to cover that first as a very basic 101. We're going to talk about why the research was done, why it matters, and what we did. And then we'll be going over some of the key findings from the research. And to close things up, we'll have some highlights from case studies, which there were 5 case studies. And we have 2 folks today, Owen from King County Metro and Tim from the TTC, who are going to give us a little bit of a deep dive into what they're doing at their agencies when it comes to TSP. We'll spend a little bit of time on future research needs. And then, as Lori mentioned, we will have some time at the end for question and answers. And we hope to hear your questions. Our goal today is not to go into, highly detailed technical issues when it comes to TSP, although you'll see some of that from Owen and Tim when they talk, but to give you an overview of TSP and what we found in the synthesis work. So first, we'll talk a little bit about what is transit signal priority, or TSP. And the image there provides you with some of the basics. The image shows one version of a systems architecture for TSP. But basically, the bus has to, in TSP, the bus communicates via some mechanism, some technology, to a signal, a traffic signal, and the traffic signal will make a decision as to rearrange timing in some way to try to reduce the amount of delay the bus is going to experience at that intersection. TSP is not the same as preemption. And, the bus doesn't preempt the light. Not all requests for priority are granted when it comes to priority. And certainly the bus doesn't approach and then all of a sudden the signal will change and give it a green, right? So there's certain kinds of priority. We're going to unpack some of those and what's in use in the US right now. And there are many specifics when it comes to how a TSP system could be designed and how it could work. There's differences across systems in how buses communicate with signals, when buses might request priority, when signals might actually grant priority, and how signals grant priority, what type of priority they actually give. So there's a lot of specifics, there's a lot of details, and every deployment, that we've seen is a little bit different from others. So, but that should give you a basic understanding of what TSP is. Now, we're going to use some terms in the webinar today, and these terms are also used in the report, which is Synthesis Report 149. We use the term TSP system to refer to the hardware and software components and modules that are working together as a whole in order to give a priority, right? So that's the word. We'll just use TSP system to think of those things collectively. We'll talk about system architectures, which are the functional design of the hardware, software, and communication interfaces. How is the system actually put together? What type of communication technology is being used, et cetera. That is a systems architecture. And we'll also talk a lot about business rules and parameters. When it comes to TSP, like I mentioned earlier, not every request for priority is granted. And the decisions and the rules for granting or requesting priority, we call those the business rules. Those are the business rules of the TSP system. When should a bus ask for priority, and when should it be granted? Parameters are the specific values that are associated with a business rule. So if there's a business rule that buses have to be late before they ask for priority at an intersection, well, the parameter is how late, right? Is it 1 second late, 20 seconds late? So the parameters refer to those specific values associated with business rules. We also are going to use the term deployments or deployment group today, which is our terminology for a collection of routes or buses or intersections that all share a common TSP system. Some transit agencies that are featured today or responded to the survey for our research, had one deployment where they deployed TSP, a TSP system on one corridor, and that's all they have. In some cases, TSP might be rolled out on multiple corridors, and there's actually different systems supporting the TSP. And so those are considered different deployment groups. And so you'll hear the word deployment today, also during the presentation. Just wanted to help clear up what those terms are. So I'm going to talk a little bit about why this research was even done. And if you're familiar with the Transit Cooperative Research Program syntheses, the goal of a syntheses are to synthesize what's happening right now in the industry. And when this research was sponsored by TCRP, and even today, there is continued growing interest in transit signal priority. TSP, if you peg sort of the dates, it starts back, all the way to the 1970s. It has changed over time as technological advances, particularly in wireless communication, as well as in vehicle locationing, right? GPS and knowing where buses are and knowing the status of buses. All of these technological advances have improved TSP since its original configuration and rollout. And there have been many deployments of TSP in the last 10 to 15 years. And you can find in Google, news articles and stories and capital programs and plans where agencies are exploring and deploying TSP on certain corridors. With this growing interest, there's a big question is, well, is TSP really useful? And the bulk of the evidence that we've seen and that agencies are seeing is that TSP can be a useful tool to improve travel time, to reduce the amount of delay buses have at signals. By doing so, it can actually lead to reliability improvements so that the travel time a bus requires along a corridor might actually be less variable, right? So rather than taking somewhere between 50 to 75 minutes, to get through this corridor with TSP, there might be an improvement on that where it's maybe only 50 to 60 minutes or something. And so seeing those reliability improvements is great. And TSP can be configured to be a real-time tool that actually is reacting to existing conditions on the route. So if a bus is getting late, TSP can respond to that and try to correct that lateness. So definitely is a tool in the toolbox for transit agencies. But as agencies are trying to roll out TSP or thinking about TSP, there's a lot of questions, right? And the last nationwide assessment of TSP deployments that we could find dates back to 2005. And there is a lot of information, from NACTO and many other resources about how TSP can work and how it could be configured. But a lot of it boils down to, disparate case studies from different agencies. Here's how they did it. Here's how they did it. So the need really was, we need an up-to-date synthesis of information on what's really going on right now in the U.S., in North America, in the TSP space, and what are agencies doing right now, and what appears to be effective based on what they're doing. And those really laid out the goals of the synthesis study. We really wanted to just first understand, what are the recent deployments and innovations when it comes to TSP. What are agencies doing right now when it comes to their business rules? Are they granting priority based on lateness? Are they granting priority based on headway deviation? What are agencies doing? And so we wanted to get that together and look for successful practices. What seems to be working best? And then hopefully the study will serve as a resource for agencies that are considering TSP and give some background and evidence of, hey, these agencies are using TSP, this is how they set it up, and this is the effectiveness that they saw. And so in order to accomplish those goals, it's a 4-step process. We did a literature review. We tried to identify transit agencies in North America that appeared to have a TSP deployment. So we surveyed them. We have a bunch of survey results from those agencies. And then we also completed 5 case studies. And you'll be hearing from 2 of those case study agencies today. And all that got compiled into Synthesis Report 149, which is available free for download from the TCRP website. So I'm going to turn it over now, and I've given you the background about why the study actually was undertaken. I'm going to turn it over to Paul Anderson, and he's going to share with you the key findings today.
So hi, my name is Paul Anderson. I've been working at TTI for a little over 2 years, and my background is in transit operations and traffic operations research. So first we'll start with a map, and this kind of gives you an idea of the agencies that responded to our survey. And the size of the circles shows you how many vehicles that they operate in maximum service. So as you can see, we had a pretty good coverage of different regions of the U.S., a few Canadian agencies, and a pretty good distribution of size too, from smaller to some of the largest agencies in North America. So the first key question on the survey was whether they're currently operating TSP in a full deployment. And so we had 46 agencies that responded to the survey, and 28 of them, or 61%, have an active TSP deployment, and 39% do not. But of those that don't have an active deployment, many of them were interested in TSP or even actively pursuing it through a feasibility study or a pilot test. So one of the key distinctions that emerged in our literature review, and we had several survey questions on, was the system architecture, or how different hardware is connected to allow buses to communicate priority requests to signals. And so several different architectures are possible. One of the alternatives broadly is a distributed system where buses are either detected by or they communicate directly with traffic signals. And some of the technologies that can enable this are sensors in the pavement, like loop detectors, infrared, or in the future, possibly this could be done through dedicated short-range communications, which is being proposed as kind of the platform for connected vehicle and vehicle-to-infrastructure communications. And so this distributed setup was used by 77% of the deployment groups in our survey. And the other big grouping is centralized architectures. And so in a centralized architecture, priority decisions are sent through a centralized management center, which could be the transit agency's management center, or it could be a traffic management center that's managed by the signal owner, or potentially involving 2 centers. And so in this type of system, the buses' location is tracked continuously through AVL, or an automated vehicle location system. And the signals would have to be linked to the center in some way. One way of doing this is through fiber optic cables. And this kind of setup was used by 23% of the deployment groups in our survey. One of the other key distinctions is whether there are any operational status requirements that buses have to meet in order to request priority. So in our study, 13 respondents said that buses do have to meet a condition before they're able to request. The most common condition, which all 13 were using, was schedule deviation. And so this would say that a bus has to be behind schedule, either behind at all or behind by some amount. And that's the parameter value, which is also in our report. One thing that was mentioned in several research studies was that this could be done by headway deviation as well. We didn't capture any agencies in our survey that were currently doing this, but we did capture 2 agencies that had a passenger load requirement. And so this would say that a bus has to be carrying a certain number of passengers, otherwise it's not eligible for priority. But overall, the majority of the agencies that responded, so 18 of 31 deployment groups, were not using any operational status condition. And so there are several different types of priority that buses can receive when they send a request. These are explained in more detail in our report, including diagrams that show the signal phases and how they will be rearranged to give a bus some priority. But broadly speaking, the most common one, which 28 of 31 deployment groups used, was an extended green, which would just hold a green light a little bit longer to give the bus time to get through. And so in general, one of the topics that comes up a lot with TSP is a negotiation about how much priority buses should receive, because the more priority that's given to transit has some implications for other road users like cars and pedestrians. And so when many TSP systems are deployed, other stakeholders will ask for some limitations that kind of cap the amount of priority that transit can get. And so the most common type of limitation that came up in our survey was a lockout period. And so what this means is when a bus is successfully given priority at an intersection, then priority would be unavailable for any other bus for a certain period of time. And that kind of allows the signal to return to its normal timing and flush some of the queues of cars or people waiting that have built up while the bus was going through. And other types of limitations are locations. So some intersections could just be exempted even though the rest of the corridor has TSP. And there are also other limitations like direction, day of week, time of day, or potentially service type, like maybe only some buses on a corridor would be able to get TSP. So one of the questions we had on our survey was qualitative assessment of benefits. And so we asked, what benefit has TSP had on several typical performance measures? And this is on a 1 to 5 scale, where 5 is the highest level of benefit and 3 is neutral. So all of these performance measures came out positive. People reported the greatest benefits from TSP in reduction in intersection delay experienced by buses and in travel times. But there was also positive ratings for schedule adherence, headway adherence, travel time variability, and headway variability. And one of the analyses we did in processing the survey results was to group agencies, or rather deployment groups, by the amount of benefit that they reported on some of the qualitative questions. And so one of the things that emerged from that analysis was this table, which suggested that the agencies that had more priority types available to buses were also the ones that were experiencing more benefits from TSP. And so drawing from both the survey results and the case studies, we came up with 4 common threads of many successful deployments. One is that TSP involves a lot of coordination between the transit agency and other stakeholders. Often the cities are the ones operating traffic signals. Sometimes it's the State Department of Transportation too. And sometimes MPOs or metropolitan planning organizations also get involved. So there was certainly an element about coordinating responsibility and priorities among multiple stakeholders. Successful agencies also did constant monitoring of software and hardware changes. Sometimes this will be upgrading from one type of location tracking to another, or just doing regular software updates to the whole TSP system. There was also a common thread of it's important to select appropriate business rules and parameters, and also to refine these over time. So we heard from several agencies that it's hard to get exactly the right parameters without having some experience operating the system. And so it's important to evaluate TSP systems early, so right after they're deployed to see if everything's working as intended, and then continuously, and to keep making tweaks to parameters if things are starting to shift and not work as well as they used to. And another qualitative question that we had on the survey was asking agencies to rank various challenges that are common and perhaps mentioned in the research literature as well. And so this is on a 3-point scale where one response is that this was not a problem at all, another that this is a slight problem, and a third that this is a major problem. And so the two challenges that came out on top here were in measuring the TSP system's benefit. There was a lot of uncertainty about the best way to do that, or perhaps collecting the right data to be able to do that. And then another topic that was ranked highly by a lot of agencies was the challenge of maintaining TSP operations in the long term, because it involves a lot of stakeholders, and there may be changing priorities or budget pressures and recessions and et cetera that all make it difficult to keep the same level of performance. And so this is just a sampling of what you'll find in the report. Some other report features are, we had a lot of questions on the survey about specific parameter values, like if an agency requires buses to be behind schedule in order to request priority, well, how far do they have to be behind schedule? And so we have distributions for that parameter and several other common parameters. We also have listings of vendors that different agencies are using for both their TSP system components and the traffic signals. There's a discussion of other factors that may influence how much benefit buses get from TSP, like stop location. In particular, nearside stops are a little bit challenging and take some customization to get TSP to work in that configuration. And then other things like bus-only lanes may also help or hurt TSP. And so we also had some discussion of performance monitoring, what performance measures are other agencies using, what's been suggested in the literature. And then finally, there were some survey questions about the capital expenses to set up the TSP system, as well as the operating costs and maintenance to keep it running. And one other resource that we'd like to highlight is there's this big summary table that you can find in Appendix B that lists all the deployment groups in the survey and some of their key parameters. And so the next phase of this webinar, we'll hear from two of the case study agencies. And so with that, I'll turn it over to Owen Kehoe.
Thank you, Paul. Let me get my screen shared here. All right. So yeah, my name is Owen Kehoe. I'm a traffic engineer at King County Metro Transit in Seattle, Washington. I work in a group called Speed and Reliability, and I've been working on TSP for almost 20 years now, kind of doing everything from planning to design to implementation and sometimes maintenance when needed. So today I'm going to just talk, first I'm going to share kind of some King County facts and show you where we have TSP deployed. I'm going to talk about our TSP system architecture, the TSP goals that we've employed, specific TSP strategies we've used. I'm going to outline a negotiation process that we use with our city partners and kind of how we get these, how we agree on what we're going to do. Then I'll talk about some of the benefits that we've measured, and then kind of a preview of looking towards the future of our next-gen TSP system. So for those of you not familiar with King County Metro, here's a quick facts and figures. We are the primary transit agency serving Seattle and the surrounding area. Our fleet size, we have a little over 1,600 vehicles. That includes electric trolley buses, diesel electric hybrid buses, and we have a few battery electric buses. Just yesterday, we retired our last diesel only coach, so we consider ourselves a fully green fleet. Before COVID, we had about 400,000 daily weekday boardings. Of course, that's lower now. Also, Sound Transit is the regional transit provider, and we operate their light rail trains, streetcars, and and Sound Transit Express buses. Also, there are 39 cities in King County, as you can see in this map here, and almost all of them have some form of transit service. So for TSP, we currently have it deployed at a little over 200 intersections. These are mainly on the rapid ride corridors. Rapid rides are BRT service. So we have the A through F lines. And then we have it on a few other high ridership corridors. Of these locations, we work with 13 cities or jurisdictions, including the state DOT for TSP. And the controllers we use currently, mostly we use the Siemens M50, M60 controllers. That's what Seattle uses. Some of the suburban cities use the Econolite ASC3s and Cobalts. The state DOT uses 2070s running Intolite MaxView. And we have a handful of peak ATC 1000s in the city of Seattle, although those are gradually being phased out. This is a quick diagram of our TSP system architecture. So basically, the way our TSP system works is the buses have the 4.9 gigahertz public safety band radio, and they communicate with these roadside wireless access points, which are connected inside of a dedicated cabinet to King County-owned communication equipment. And this also runs real-time arrival signs and our off-board fare processors. And then within here, we have our custom piece of hardware called the Transit Priority Request Generator. So basically, the CAD AVL system on the bus, when the bus reaches a predetermined check-in point, it will send kind of a message over the network to this Transit Priority Request Generator. And this processes the business rules, and then we'll place the call to the signal controller. This is what the equipment looks like in the field. We have the wireless access point kind of mounted high up on the mast arm. This is the Transit Priority Request Generator. It's basically a modified McCain ATC controller with special software. This is the interface panel that integrates with the signal controller. And this is our dedicated cabinet. So we call this a stretch cabinet. It's basically a signal cabinet with the signal equipment in the lower level. And then we have this upper cabinet that houses all the King County equipment. So as you can see, this is all pretty infrastructure heavy. It's rather expensive to deploy at the TSP intersection. And so we're looking at replacing this with a centralized system, which I'll get into later. So as far as our TSP goals, initially our first goal was to improve travel time. Basically, we wanted to reduce those travel times, and to do that, we wanted to give every bus TSP whenever possible, with kind of the ultimate goal of having the schedule reflecting the benefits of TSP. So here you can see an evaluation of this strategy. This is travel times kind of split up by in-motion, dwell time, and signal delay. And you can see we've been successful in reducing the signal-related delay with TSP. The disadvantage of this goal is that the traffic agency will be concerned about the signal being interrupted every time. So it kind of limits the amount of benefit we're able to get through individual TSP calls. A newer goal we've been doing is a reliability-based goal. So basically, instead of trying to give every bus TSP, we're trying to focus on those late buses and getting those through faster with the goal of improving either on-time performance or headway. So this shows kind of a way that we would measure that. So on the Rapid Ride C line, we have a goal of 80% of the buses meeting the headway, and this kind of shows how that's gone over time. And so we're trying to get this as close to 80% as possible. So the advantage of this strategy is that the local agencies may be more willing to accept more disruption if it's not happening with every bus. So now getting into some of the strategies we use, we have what we consider standard TSP strategies. These are kind of like the ones that Paul described. You have green extensions, early greens, or red truncation. In some locations, we do what's called full priority. That's a Siemens term. It's basically allowing phase skipping. The business rules we use, we have route eligibility, so generally only specific routes are eligible for TSP. We have to provide a recovery period after one TSP activation. Usually that varies between 60 seconds to 5 minutes. And of course, we can't violate any minimum greens or vehicle or pedestrian clearance intervals. Some of the more advanced strategies we've used are, in some locations, we've done a tiered request level. So basically, whether the bus is on time or late, it'll request a different level of TSP. In some locations, we proposed doing cascading priority. So if you have a bunch of intersections that are close together, one bus will chuck in multiple intersections at the same time. So far, we just had been able to do this in theory. We haven't been able to deploy a cascading priority system yet because it requires a pretty complex peer-to-peer setup at the signal controller level. We just haven't been able to get that up and running yet. We also do priority at nearside stops. And the way that works is we have the bus check in before the bus stop. And then we look at our historical dwell time for that bus stop. And we try to predict when the bus will leave that bus stop. And that's get programmed into the controller as this time of service desired setting. It's basically an ETA. And so this chart just kind of shows how we plot the dwell time, and we're looking at that. This is a cumulative dwell time distribution. Some of our city partners have installed adaptive signal control, and we have successfully integrated TSP into those. In Seattle, they run Scoot, and Scoot has a pretty extensive set of being able to do extensions, red truncations, phase skipping. And we've tested this at just one location so far, First Avenue North and Mercer Street. But there'll be more of these to come in the future. In the city of Bellevue, they run the SCATS system. And unfortunately, it doesn't do TSP out of the box. So we've had to kind of jury rig it by adding extra stages that provide those green extensions and early greens. And basically use a detector call then to call that special stage. In the city of Renton, they run ACS Lite, and it does kind of the standard extensions and truncations. So now I'm going to outline what I consider to be a 4-step process for negotiating the TSP strategies with the local agency. And I think we've been pretty successful in using this process. So the first step is agreeing on the overall project goals. So like, what are we trying to do here? Are we trying to reduce travel time? Do we want to improve reliability? Which routes are we going to focus on? And so these are pretty high level discussions, involving directors, planning staff. A lot of times in some of the smaller cities in particular, the traffic engineers may not be so keen on TSP, but sometimes we'll find an ally in the planning department. And we do that, then we're looking at data on like the route level performance to help inform these decisions. Then step 2 is we start looking at the individual intersections and trying to decide, okay, what are we going to do at this intersection at this time of day in this direction? And then we're kind of involving kind of the mid-level manager staff. So we look at delays or look at the data about where the delays are occurring. We look at traffic volume to capacity ratios and pedestrian activity, particularly if we're proposing phase skipping. And like I said, we really get down into a fine-tooth comb and defining what strategy is used by direction and time of day. And the key outcome of this is that we come up with a spreadsheet that kind of documents all these decisions. So this is a kind of an excerpt of the spreadsheet. So we've got all of our intersections listed, all directions, and then by time of day, we're documenting which strategy we're doing, and if it's a lateness strategy, it's like how many minutes late does it have to be to trigger the late strategy. Step 3 then is where we we bring in the signal operations engineers, and this is where we really get into what actually gets programmed in the signal controller. And basically, we're using that spreadsheet we did in step 2 as a guide. One of the things we found is that these signal operations engineers, they tend to be pretty reluctant to do anything to upset their carefully crafted signal timing plans. And so if we do our homework in step 1 and 2, then it kind of helps provide some motivation for the signal operations engineers to really follow that. With some of our smaller cities, we can bring in outside expertise, either in-house or consultants. Some of them may not be as familiar with the TSP settings, so that's been helpful. And then this is a iterative process where we'll implement something in the field, and then we'll watch some buses go by, and then fine-tune the settings as needed. And we do record these in a spreadsheet, although what we found is kind of once we walk away, the agency will often change settings without letting us know. So those spreadsheets aren't all that useful. And then, of course, the 4th step is operations and maintenance. So we can't just let the system run by itself. We do have issues that arise. Here's an example of a type of issue that we have to fix. And besides these kind of issues, we'd like to be able to retime the TSP every 6 years. Unfortunately, it's become a real challenge to get budget available for TSP operations and maintenance. So unfortunately, we haven't been able to maintain our retiming program. So some of the benefits that we've measured from TSP, this is under the original travel time strategy. We generally see kind of a 15 to 20% reduction in signal-related delay, so just looking at that signal delay. And with the overall travel time, we see kind of around 5% reduction in travel time. And so these were measured by turning the system off for a week or two and then turning it back on and kind of comparing the on and off data. And with our more recent reliability strategies, we did this most recently in 2018 on our rapid ride C and D lines. And there we implemented the tiered request level, where the level of TSP is based on the lateness of the bus. And I put lateness in quotes because the rapid ride lines are actually a headway-based system, and their performance is measured on headway. And so our goal was to reduce headway, but we didn't have, our CAD-AVL system didn't provide any information on headway. We only had a lateness field. So that decision has to be made based on lateness. So on this, what we see, kind of looking at the all-day picture on both lines, we see a 6% reduction in buses that are missing that headway target. And in this case, the headway target is being within 2 minutes of the scheduled headway. But we saw pretty significant, even more benefits on some of the PM outbound trips during kind of the afternoon commute. So on the C line, we saw up to 30% reduction. And I should note that this was not an on-off study. So this was kind of comparing our previous strategy of reducing travel time with our new reliability strategy. And so these are kind of in addition to the travel time. And then looking towards the future, where we're planning our next-gen centralized TSP system. So the way this is envisioned to work is the buses will use a cellular connection, and they'll have a constant location ping. So about once a second, they'll be sending their location to a central server here. We'll then process that data and kind of add additional fields, and then send that along to the local traffic agency's central server. We're kind of calling this like our subscription service, where basically the local agency will subscribe to a data feed from King County. And then the local agency then will generate the requests and process the business rules, and then those get forwarded along the city's traffic network out to the signal controller. So the advantage of using this centralized system, the big one is that we don't have to put in all that expensive roadside equipment and maintain it. Also, we're not building a duplicate communication network. So the cities have done a pretty good job of communicating and building out their fiber network to their signal controllers. So we might as well use that. Also, most of the signal vendors have a centralized, kind of off-the-shelf centralized TSP product that we're able to use, and so we don't have to reinvent our own central system. And then we hope the system will have improved accuracy and reporting capabilities. So the system we're hoping will be ready towards the end of next year. All right, so I'm going to hand it off now to Tim Lawson from the Toronto Transit Commission.
Thank you, Owen. I'll share my screen. So my name is Tim Lawson. I'm a senior transportationeer. I've been at the Toronto Transit Commission for 20 years. And during that time, I've been working on TSP and other transit priority measures. Today, I'll describe you the role of surface transit in Toronto. I'll go through some of the high-level summary of TSP system features in Toronto. I'll talk about some notable practices that we do and some lessons learned. So the City of Toronto has a population of about 3 million, and the Greater Toronto Area itself is about 7 million. The Toronto Transit Commission is an agency of the City of Toronto, and we operate subway lines, streetcar routes, bus routes, and a paratransit service within the City of Toronto. Also serving the City of Toronto proper is GO Transit, which is an interregional rail and bus service. There are also 7 local transit authorities in the what's in the blue region shown on the map here, some of which operate a little bit into the City of Toronto, particularly connecting with the subway. So the role of the TTC. The TTC is huge in terms of the ridership in the GTA. About 75% of all transit trips in the GTA are carried on the TTC. And that results in over 500 million annual customer trips. So this places the TTC as the second highest ridership of a transit system in the US and Canada after New York. This equates to about 1.7 million trips on a given weekday. But in terms of bus TSP, we're looking at surface transit trips. So about 70% of our trips, so about 1.2 million daily customer trips on the bus and streetcar network. And because we have such high ridership, we actually have almost 20 what we would consider very high ridership corridors of about 30,000 customers per corridor every weekday. Due to this high ridership, in the City of Toronto's official plan, there are very transit supportive policies. And also because of the extensive use of transit, we were a very early adopter of TSP starting back in 1990. So you probably will not be surprised that on our streetcar corridors, 6 of them have over 30,000 daily riders on a weekday. It's on the bus network, where you may be more surprised to learn that we have 13 corridors that carry that level of service, and it's all across the City of Toronto. So our TSP implementations to date is about 400 intersections since our pilot. About 200 on 7 streetcar routes in the older part of the city, 200 to date on 4 major bus routes, and we have several locations where we have isolated transit signal priority, mainly to accommodate buses making left turns. We have a distributed architecture at the TTC because we started with streetcars. We decided to piggyback off our existing radio frequency transponders that are on every streetcar and are used for track switching purposes. We use check-in and check-out detectors that are embedded into the track bed itself. And historically, we've run overhead cable on our own streetcar poles back to the traffic signal controller. We had Novax create a custom streetcar receiver module to receive these signals from the transponders, and then the TSP calls go into the traffic signal controller. So this has provided us a very accurate and reliable detection system, assuming, of course, that the loops and the feeders are not damaged due to construction. Around 1988, we worked with Novax again to develop a bus transponder that would be compatible with the streetcar receiver module, and that's it on the underside of the bus. Again, we used overhead cables back to the streetcar receiver module and the controller. The big difference being, of course, we don't have streetcar poles on the bus network. So our overhead cable was on Toronto hydro poles. This has been a challenge because for several years now we've had issues trying to get pole attachments compared to what we were able to do in the early days of our implementation. We have done limited locations with wireless communication back to the traffic signal cabinet. So for our business rules, at a high level, we do extensive use of green extensions. We've done a lot of development that I'll go into in a couple slides. We do early greens. We don't do it in as many locations as some cities, primarily because a lot of the signals we operate through are already at the minimum pedestrian signal timings for the side street. And in Toronto, there are a lot of pedestrians and a lot of pedestrian calls. We have extensive use of phase insertion for streetcars and for buses. We have a type of sequence change or phase rotation because we often allow multiple insertion points for transit. So we have a very old system, and it was never impractical based on our legacy AVL system, our vehicle location system, to have a type of schedule-based priority. It just simply wasn't accurate or reliable enough. We're moving to a new system, so things may change with the new system. Historically, we haven't had a lockout of TSP calls following the previous TSP call. There are some exceptions in what we call the priority operating zone when a vehicle is between the check-in and the check-out loops. If a second vehicle enters, and that's very common because we have very low headways of 3 minutes or less, the second vehicle is essentially invisible. We also have implemented lockouts for the specific case of streetcars at far side platforms to prevent a following vehicle from calling an extension unnecessarily because they'd have nowhere to go. But we do require approval for each intersection from our partners at the City of Toronto Transportation Services. So we need approval for every intersection where we propose TSP. There are also some cases where we do different types of TSP by time of day. And we actually have many different conditions and logic built into the controller, and I'll address that in a few slides. One big difference that Toronto has is for most of our green extensions, we have a 30-second maximum extension as required. And this is based on the very transit supportive policy, recognizing the importance of transit in Toronto. And it allows us to adjust for variabilities in passenger service time or dwell time, given that most of our stops are near side of the intersection. We actually designed TSP based on a 14 to 20 second design extension, so we have a little buffer. The maximum extensions are not restricted by signal coordination. Coordination is interrupted, and then we use a sophisticated recovery mechanism to get back into coordination. But it's important to remember in the Toronto context, for those of you not familiar with how streetcars operate, because all traffic must stop when streetcars are loading and unloading in the live lane of traffic, coordination is already significantly impacted just by the nature of having streetcars run every few minutes. It's important to know that, that because we don't restrict it to make sure that the controller's in signal coordination, this is a very different approach than what's used in a lot of traffic signal controllers that do sometimes limit maximum extensions based on spare capacity in the cycle or the side street. So we've done a lot of work developing TSP functionality because back in 1990 there weren't a lot of options. And the City of Toronto had a main traffic signal system, which was a centralized traffic signal control system. And Metro Toronto staff and TTC staff worked together in-house to develop TSP. Originally, it was actually using preemption, but with very specific rules and recovery routines to mitigate the impacts. So we worked over the years with the now City of Toronto to develop more advanced algorithms based on their changing policies and the capabilities and constraints of MTSS. When the city decided to replace their MTSS system with a central monitoring system, we looked at the controllers that were available and the functionality, and none of them came close to the functionality that we already had under our existing system. So this led to the city and TTC putting out a request for quotation for a controller manufacturer to do the custom development of TSP into one of their controllers based on our specs. And this ended up in all the features that we were interested in and more being developed into the PKTC 1000 controller. So in addition to the improved TSP functionality, the recovery mechanism has become much more flexible and responsive to mitigate impacts to other road users. So I want to talk to you about the green extension algorithms we've developed because it's very different from what is done in other cities in North America. But to understand this, you need to understand about the pedestrian clearance interval. So this is what we call the flashing don't walk in Toronto. Some people may call it the flashing hand. The important thing to know is in Toronto, as most places, the flashing don't walk is never extended or shortened for a particular intersection. The flashing don't walk is fixed for a given pedestrian crossing at a particular signal. So what are the options in terms of providing a green extension? We can't do it during the flashing don't walk. We do it either before, during the walk and green, or we do it after the flashing don't walk during what we call the solid don't walk. Some people call it the steady hand with a green signal. So we have four main algorithms that we use. The simplest one we just call the solid don't walk algorithm. As you can imagine, we don't have any extensions in green and walk. The flashing don't walk is fixed, as I mentioned, and we will allow up to a 16-second maximum in solid don't walk. So that's less than the 30 I mentioned before, because when pedestrians face a green signal with a solid don't walk, if it is too long, it can increase the chance that they will decide to walk regardless of the display. So that's why it's limited to 16. To get around this, and that is the most common algorithm used around North America. We, many years ago, back in the early 90s, developed a walk algorithm. And with the walk algorithm, the green and walk can be extended up to 30 seconds before the flashing don't walk comes up, and then there would be no time served in green and solid don't walk. But then we developed more advanced algorithms to take advantage of the better effectiveness of the walk algorithm, but the solid don't walk algorithm is actually quite efficient from a traffic perspective. With our third algorithm, we have extensions in both walk of up to 14 seconds, a fixed flashing don't walk, and up to a 16-second solid don't walk green extension that kind of combines the best of both worlds from algorithms 1 and 2, with a total combined extension of 30 seconds. Our fourth algorithm is identical to the third, where we have a total of 14-second maximum walk extension and 16 in solid don't walk, but we have two different detection zones to do this. So I'm just going to explain to you how this most complicated algorithm works, just to give you an idea. So we normally have, as I mentioned, a check-in and a check-out loop. With this more complicated algorithm, the normal priority operating zone is split up with a new advanced cancel loop. We have zone 1 that governs the extensions in green and walk, and zone 2 governs the extensions in green and solid don't walk. So I'm going to show you what this looks like as the bus, shown by our icon, enters the priority operating zones. So this is the regular signal display. I'm going to start the clock, and you'll see the signal going through the regular sequence, starting with north, south, green, and walk. So for this algorithm, the decision point to provide priority is at the end of the green and walk before the flashing don't walk comes up. Because both zones are active, we prepare to serve up to this 14-second extension in walk. But if the bus hits the advanced cancel loop and the first zone becomes inactive, before that 14 seconds expires, we terminate the extension, let's say after 6 seconds, and go immediately to green and flashing don't walk. So the next decision point is at the end of the green and flashing don't walk. At this point, if the zone is still active, we prepare to serve a final 16-second extension in green and solid don't walk. I'll start the clock again. So once the bus hits the checkout loop, the zone becomes inactive. We terminate that extension, and we go immediately to yellow. So with this particular example, we used 6 plus 7 seconds of extension, a total of 13, which would have been far less than what it would have been using just an extension of walk in 30 seconds if there was a lengthy flash and don't walk. So our business rules in the controller, the most important is really the decision point. We will only provide an extension for a vehicle that has a reasonable expectation of successfully getting through the intersection. And we have certain parameters that we can use that delay it, similar to what Owen said, if the passenger service time could be variable. Where we have competing TSP calls, we have a first sequenced, first served approach. So if we have both eastbound and southbound calls, if we're currently serving the east-west green, we will extend it if we think that the eastbound bus can get through, because the benefit of an extension is generally much greater than the disbenefit to the southbound bus. For complementary calls, we will allow calls in both directions to come in if the calls both come in before the decision point, regardless of which one came in first. We will also skip some green and solid don't walk extensions if the controller is already not planning on serving the side street due to lack of demand, because it's unnecessary. I'm not going to talk a lot about red truncation. We can essentially truncate any phase even below the pedestrian minimum if there is no PED call. And we can even truncate the main street if that would help a bus on the side street. And partial truncations are allowed. We've done a lot of work, as I mentioned, on left turn TSP, where transit can extend an existing left turn arrow callable by either traffic, or there could be a location where only transit can call the arrow, and otherwise traffic can only turn on a regular green ball display. We have a lot of different ways we can do that as shown. We also have special inserted phases, the vertical white transit bar that's used in Ontario, and this can often come up multiple times in a signal cycle. I've mentioned we've done a lot of work on recovery and green compensation. In the old system, it would extend or reduce phase times based on preset values. With the new system, it's become much more flexible to allow the user to program various parameters as to when to extend, when to not extend, and exactly how much each phase should be extended or reduced. Oh, sorry. Hit the wrong button there. In terms of TSP design, we take advantage of the full flexibility that we had built into the controller. We will customize to the site-specific conditions, considering all these factors. And we can even customize for an intersection approach individually. If we determine that we have to use algorithm 1 because of very close signal spacing and no dwell time, we are no longer limited to use the same algorithm in the other direction. We can use a more effective algorithm, such as algorithm 3 shown here. In terms of the benefits we've received, we've, based on surveys in the past, received a benefit of about 16 seconds round trip at a given intersection on a route with 40 traffic signals with TSP. This means we've been able to save about a 10-minute round trip time on the bus route. We often get more than the 16-second benefit for left turn TSP. So in the past, we've had faster travel times. We've been either able to take vehicles out of service and maintain the same headway, or create additional capacity. I'm just going to show you some of the benefits that we've received when we've updated the timings on our King Street corridor as part of using the new controller and using its full functionality. At King and Bathurst, with combining left turn TSP and through TSP, we've had a major reduction in delay eastbound, particularly the maximum delay. But throughout the King Pilot corridor, and you may have heard of our King Pilot that was a few years ago, we've been able to develop parameters to address one of the city's biggest concerns, which was pedestrian delays. So we picked offset recovery parameters to mitigate and minimize impacts to pedestrians. Our lessons learned. From our perspective, the benefits from TSP are entirely dependent on the signal controller's functionality with respect to TSP, recovery, and compensation, and also the level of priority granted and any extent of conditions imposed. It's very important because there will always be challenges, as Owen alluded to, regarding competing priorities between the transit agency and the traffic agency. So it's important to have high-level agreement and direction to other staff about what the level of priority is going to be and what acceptable impacts are to other road users. I guess our third lesson learned, and this probably applies to most people listening, there are a lot of misconceptions about TSP from the public and professionals alike about the intricacies about how TSP works, what the impacts are, and the available tools there are to mitigate the impacts. With that, I'll send it back to Michael to talk to you a little bit more about the case studies in other cities.
Thanks, Tim. I'm going to start sharing my screen again. And so I really want to thank TTC and King County Metro for the detail that they went into and how their systems are designed. Hopefully that piqued a lot of people's interest, and I see some questions already coming in. We hope to get more. We also wanted to highlight the other case studies. There are a total of 5 case studies in the report, and they include San Diego, San Francisco, and Rhode Island. And this slide just highlights a couple of the challenges, practices, and lessons learned that we wanted to pull out for you all from these different agencies. I'll just, rather than reading all these points, I'll just highlight just a couple that I thought were very interesting during the, from each one of these agencies. You already heard about the discussion and the importance of, stakeholder buy-in and the importance of laying that out very early on, agreeing on goals, and you'll hear that theme come up again, and just the theme of planning. And so not only at San Diego, but basically every case study agency that we talked to had some, message, some takeaway about the importance of planning, and not only on what you're trying to accomplish with the TSP deployment, but also how you're going to do it and how you're going to maintain that over time and who's responsible for doing what. And so that is really important to ensure the success of the TSP program. Some lessons learned or one at San Francisco found that bus operator behavior could influence the TSP benefits. So we didn't see this across many agencies, but at least at SFMTA, they experienced some Lawson benefit based on operators thinking that they weren't going to be able to get through the signal or not understanding exactly that they had priority. Because as you approach an intersection, oftentimes you're trying to make a judgment call as an operator about whether to go ahead and go through or whether just to hold back and wait for the signal to change. So it's important they found that operators fully understand how the priority works, and if they see that flashing don't walk or a solid don't walk, might you be getting priority at that point? A lot of times we would wait for the light to turn, and so that's an important feature or something important to consider, how operators might interpret that. We also heard a theme that was brought up by RIPTA, Rhode Island, just this ongoing investigation of business rules and parameters, continually looking at ways to better optimize down to every single intersection, and then of course through your entire corridor, and always looking at that and tweaking in order to make the business rules and parameters really align with what's happening on the corridor. And so there's just a few key highlights from the case studies. Of course, in your handout, you can look over those, and we have that exact same table with a little bit more details in the full report. In the very end of the report, we also talk about some future research needs. And these are identified by the team as we talked with the case study agencies, looked at the survey responses, and as well as communicated with the research oversight panel. And these are just a few highlighted ones that we want to bring to the attention of folks. One is a need for better tools and manuals that could be used for TSP. And those tools and manuals, we believe are important, one, to really help establish some checklist or standard processes that work well. You saw Owen, had his four-step process for negotiating rules and parameters and establishing them, documenting them. Those types of things I think would benefit the industry quite well if we standardize those and make it easy for transit agencies and traffic engineers to follow and to fully understand, as Tim mentioned, the intricacies and the nuances and the trade-offs that come with TSP. In line with that need, we think there's a need for some more opportunities for standard training about transit signal priority. The manuals and things are always great and very beneficial, but there's nothing quite like workshops or other types of ongoing training opportunities where to help establish a standard language and a common understanding for TSP implementation, TSP evaluation, operations, and maintenance. And we think that is a need in the industry. Standardizing how to quantify TSP benefits. You all saw several examples of, quantification of benefits from Toronto, from King County. We had a survey question that asked people to report, their benefits, but really standardizing how we as an industry quantify the benefits of TSP, whether it's through intersection delay, how do you do that through on-off studies, how do you measure the benefits without baseline data, just really developing some standard ways so that, across agency we can start to see, apples to apples comparisons in place. We also think there needs to be some investigation in non-conventional, I put that in quotes, uses of TSP. There is often discussion that nearside stops, for instance, are simply not effective. You can't have nearside stops with TSP. But as you saw from both of our case study agencies, they both use TSP at nearside stops. But however, it might take a little bit more work in order to make it effective. And so there seems to be a need for more research and work there, as well as how to use TSP in the headway management application. All of the agencies that we surveyed used, if they used a condition to request priority, buses had to be late or, some combination of factors, but no agencies used headway deviation, i.e. I wanted a bus every 10 minutes, but this one is, 15 minutes. And so using TSP to stabilize headways in the academic literature is seen as a tool, but in application, we didn't see any examples of it. So we do think there's more need there, as well as lastly, just how to incorporate TSP in advanced signaling work, whether it's signal progression, dynamic timing of signals. And as you saw today, TSP can work in those kinds of situations, but there needs to be probably some more work in order to help agencies and traffic engineers work through the complicated issues when you're getting into advanced signaling approaches. So before we go to the Q&A, just want to do a quick shout out to all the folks that helped, the 5 case study agencies who you see listed here, as well as the oversight panel from TCRP itself, as well as all the survey respondents. Of course, don't get really called out here, but definitely thank you. As a plug, as you hear, you get questions from researchers about, answering this survey. We certainly appreciate. We know you guys take time out of your day in order to get this stuff done, but it makes for very useful information for the industry. So we definitely want to thank you. With that, I'm going to turn it back to Lori, who will be moderating the question and answer session.
Yes. I see that a couple of the questions were answered. Anyone listening, if you find the Q&A box, you should be able to see the open questions and then the answer tab. I believe you should have access to the ones that were already answered. They were typed in. So we'll start I'm going to start with in the order they came in. So some of these are going to harken back to the earlier part of the presentation. The first question, which is from a while ago, asks, are limitations only a function of centralized architecture systems?
So that's a good question. I'm going to chime in, but you all can correct me if I get wrong here, because I am not certainly the system expert. But if you're referring to limitations on granting priority, for example, locking out an intersection and not allowing it to grant priority for a certain amount of seconds or a certain number of cycles. If that's what you're talking about, the limiting function of is not related to whether the system is centralized or not, but really just the capabilities of your controllers and whatever logic is built therein, what they can handle. And if anyone else on any of the panelists have any other insight into requirements for limitations of priority, feel free to chime in.
Sure, I'll chime in. So I think some of the limitations and priority conditions are a little bit easier to check on the centralized side because you're doing checks sort of on the transit agency's management center. So there's a greater data availability and computational power. But certainly some things can be checked in the signal cabinet. There's just a limited computing resources there.
Yeah, I would just add that, yeah, there are definitely limitations for all types of systems, and I referred to it a little bit earlier. Like there are some controllers that may only allow you to do a maximum extension equal to the unused green time or the time above the minimum timings for other phases. So that there can be some pretty significant restrictions.
Great. The next chronological question is, this is, any questions related to how bus schedules are developed with regards to the success of TSP?
This is actually a really interesting question. I saw it come up, and I think there's a related question also came from someone else about, TSP for schedule adherence, right? And there is an interplay. We actually mentioned this in the report. If you're using transit priority and you're in a corridor, but you're only calling or asking for priority when buses are late, when buses are late is a function of your scheduled speed, right, through segments of the corridor. So we didn't see much evidence of transit agencies saying they had a problem, right, or they were challenged by trying to optimize their schedules in relationship to their TSP deployment. But it certainly came up as a factor that needs to be carefully considered. If you set your scheduled speed as too generous, i.e. Too slow, for instance, and the bus is really never late to begin with, you'll never be calling priority. You never be asking for priority. If you set your scheduled speed too aggressively, i.e. Too fast, then your bus is always asking for priority because it's always late. And so there definitely is a trade-off, and it's kind of a nuanced issue. I'd like to have Owen from King County talk a little bit about how they experienced, the trade-off between schedule design and priority request. Was that a challenge that you all had at King County?
Yeah, like I mentioned on our travel time goal was to have the schedule reflect the TSP benefits. And whether we achieve that is really difficult to tell. I don't think the on-off study really captures that, whether we were able to achieve that or not. One other challenge we have with our schedulers is the way they schedule a route. They tend to put less time at the beginning of the route and tend to pad more time at the end of the route. And they kind of do that like to help the operator, make sure they get all their break, but not putting too much time in the head of the schedule, so they have to operate slow down. So there's a lot of those nuances that go into the schedule that makes it really hard to kind of tease out the relationship between TSP and the schedule.
Yeah, and for that particular item, it's better to have some scheduled recovery time instead of having it built into the driving time. Otherwise, as Michael said, the bus could constantly be ahead of schedule and wouldn't be getting any priority.
Thank you.
I think the next question was related to that. It says, does the rapid schedule rely on getting priority in order to be on time? So.
Yeah,
Right. Yeah. Go ahead, Owen. Sorry.
Yeah, that must be a reference to Rapid Ride. Yeah, again, that's hard to tell. With reliability strategy, we try to meet that that 80% headway goal, and we do see after we implemented the reliability system that we did achieve close to that goal. One of the things, if you remember that headway chart I had that said that to show that we're not meeting that headway goal. And so what that means is that there's some operating costs needed to fix that. And a lot of our routes have kind of an unmet schedule reliability operating need that we just don't have enough money to kind of fix all of the reliability issues. So we definitely see this helps. It doesn't solve all the reliability problems.
Okay, the next question. I'm trying to see the timestamps. Okay. Do any of the agencies have issues with maintaining the fiber underground, knockdowns, etc.?
We don't have fiber. I made a reference to our loops can get cut. And that is a problem. If we do end up going to a new system in the future, it would be wireless based. GPS based with wireless communication, either center to center or vehicle to infrastructure.
And we do have fiber, and there are issues. I showed you that slide of the cabinet getting hit by a car. So that we tend to get like one of those every 6 months or so. And so, yeah, that is a cost. And so we're trying to move away from maintaining our own fiber, instead relying on the city's fiber.
Huh. Okay. The next question is, how did Toronto measure the travel time savings at each intersection?
So what we did in the olden days, we did just speed and delay survey. So we ran the bus or the streetcar without TSP, and then adjusted the schedule. Once we turned on the TSP, we were able to demonstrate not only what the delays were, but the types of delays. Was it signal delay? Was it delay associated with serving customers? Or were there other factors? For some of the recent data that I put up, we had a chance for the King pilot where we had the TSP turned off for a period of time. So we recorded the actual travel times at individual intersections and then compared it before and after TSP was turned on.
Yeah, we do a similar thing. We've done the on and off study. The way we measure intersection delay is by comparing the check-in and check-out logs. There'll be a timestamp when the bus checks in and then when it leaves the intersection. And that's really been our best source of individual intersection delay.
Thanks. The next question I know is popular because I think it showed up in the chat box, so we're getting to it now. It says, do any of the agencies have an instance of a left turn TSP from a right curb lane? We have an instance where our buses make this movement at an unsignalized intersection.
We have that. We have it more for streetcars than for buses, but there's at least one location I'm thinking of where we have it for buses, and we have dedicated transit signals, and we use the vertical white bar. And in those cases, we have two opportunities in the signal cycle to insert the phase to allow buses or streetcars to turn.
Yeah, same here. We have a few left turn from right lane setups that they use. It's a dedicated phase. Generally uses the light rail type signals. And also I think most of those have the red bus lane treatment. So it's a dedicated bus lane that's really highlighted with that red paint.
Next question. When doing on-off studies on routes with schedule adherence, how can true travel time measurements be collected if transit vehicles are bound by schedules and sitting at recovery points? Or is this only done on headway-based routes?
Owen, you want to start
Yeah, that's kind of the issue we discussed before, where it's that kind of that chicken and egg issue with the schedule. With our system, the rapid ride is a headway-based system. I think I mentioned that we'd like to do it headway-based criteria, but the only data we have available is lateness. So there is an underlying schedule that kind of defines the headways. And under the headway schedule, operators are allowed to leave up to 2 minutes early. So I think as long as they're not operating more than 2 minutes early, we shouldn't be seeing that kind of effect.
Yeah, I think that's a problem that everyone struggles with. And really the best way to do it is to test it not running to the defined schedule that could be slowing you down, and just to see if it has to, adjustments have to be made. But there's no perfect way to do it.
Yeah, I think that's a good point too, and that harkens back to the question of just the difficulty with quantifying and isolating benefits, specifically related to TSP, and it takes some creativity. Some agencies that we've talked to discussed, relaxing schedule adherence requirements on operators, in order to get a better feel for the true travel time in the corridor, right? So, implement, to keep the TSP turned on and tell the operators, hey, don't worry about control points A or B. If you're a couple of minutes early, you won't be dinged for it. That might work on a high headway service where that might be possible. But there are, I think, creative operational ways that you can try to isolate and rule out those factors when you're trying to evaluate the effectiveness.
Okay. I thought I was going chronologically, but there's one up at the top that seems to be earlier, and I don't want to miss it. I know there's a lot of questions. I don't know that we're going to get to all of them, but this one is from Brendan. I hope it's Hemley. Sorry if I'm saying that wrong. It says, hi, I was one of the co-authors of the 2005 study. We found that there was often a challenge because traffic and transit staff not only have different objectives, but also speak a different language. Dialogue is easier if there are traffic engineers on staff at the transit agency. Did the national survey find that more transit systems have traffic engineers on staff?
I wish we would have asked that question because that's a really interesting question. And I think you hit the nail on the head in communication and dialogue can be very complicated. I think it's not only if the transit agency doesn't speak the same language as traffic engineers, but also if the traffic engineers don't speak the same language as, your, I guess you say a traditional transit operations person. And so at least what I've seen, and we're really thrilled with these case study agencies because they all had people on staff that spoke the language of traffic engineering and signal controls and timing and all that. And so I definitely believe it's a benefit. I don't know if it's a trend, a recent trend, or I don't know if Owen, and I'm reaching out to Owen again because Owen has been working on a nationwide sort of TSP discussion group and things.
Right.
What do you think about this, Owen?
It is a good question. I think there's a whole range. I think some of the larger agencies like New York and Chicago, Toronto obviously, have traffic engineers on staff. I think it's a lot of the mid to small size agencies that maybe struggle to justify that kind of position within the transit agency. But I think a lot of the larger ones do have that.
And to Brendan's point, hello, Brendan. I think it is very important for the transit staff, if it's possible, to have someone on staff who has familiarity with traffic engineering that can kind of act as that liaison.
I can also point out that I don't just do TSP. You know, our group does the full range of transit supportive treatments like bus lanes and parking removal, and so we're not just dedicated to TSP.
And we're the same. We look at other transit priority measures, but we also, some of our bread and butter is investigating traffic engineering concerns that come up from our bus and streetcar operators. They may say that there's a safety issue on street that can be dealt with through transportation engineering measures. So before we even had TSP, that's what the transportation engineers in our group did back before 1990.
Great.
Great. Okay, so we're 2 minutes away from the 90-minute mark, and there's about 12 open questions. So I don't know if you feel comfortable with people reaching out to you via email to answer the questions.
That's what I was going to say. There's our Paul and my email addresses are currently shown on the screen, so feel free to send us an email. And if we can't answer it, we of course will forward it on to, if it's directed to Owen or Tim, we can certainly forward it on to them and they can respond. So please do reach out to us. Lori, there was one other question I thought was important that was listed there.
Let's see.
From Nick. He talked about whether we include research on passive priority.
Oh, right here. Yes.
Versus active priority. We didn't bring up that distinction in today's presentation. We do talk about it a little bit in the report, although our report focuses mainly on active priority. That's when buses are actually asking for priority on the corridor as opposed to retiming signals in the corridor in order to benefit all vehicles. There are some agencies that are exploring, that a little bit more. Chicago was one where a little bit more work is being done in the area of passive priority and trying to coordinate that with TSP even. So it's very interesting work, but yeah, our report doesn't unpack that particular issue. Just wanted to answer that question.
Yeah, and I'll chime in too. So we did cover some references on passive priority in the literature review, but the direction from TCRP at our project panel was to keep the emphasis on active priority measures.
Yep, that's great. Thanks, Paul.
Okay, so I feel bad. There's still open questions, but it is 3:30 and I'd like to be punctual whenever possible. So I apologize that if we didn't get to your question, but as was mentioned, the email addresses are on your screen and also appear, albeit tinier, in the handouts that were supplied. You should have gotten an email, and I also pasted it into the chat box earlier. Does anyone have anything they'd like to add before I give my little wrap-up speech?
Nope, just a big thank you, especially to Tim and to Owen for participating today and for everyone for attending. Appreciate your attention. And go ahead, Lori.
Yes, thank you all so much. Thank you, Michael and Paul and Tim and Owen. This was a great presentation. Again, I'm sorry, we can't get to all the questions. For anyone still listening, you will get another follow-up email with a survey attached. If you could just take a few minutes and fill that out, NTI greatly appreciates your input. I will also share it with the panelists so they can see what a great job they did. That's it. Thank you, everybody. This was great. Everyone be well and enjoy the rest of your afternoon.
Have a great day.
Thank you, everybody.
Thank you.
Thank you.
Bye.